How about we wrap up 4.1 and 4.2 with the rest of these graphs and one application. So this second graph, I went and listed all the information from our previous work. I went ahead and marked my asymptotes, horizontal at 2, 2 verticals at positive and negative 2, mark those with dotted lines. Then we go to our calculator to determine where we're going to place those curves. So I went to my calculator, put it into y equals, graphed it, and notice I've got a curve in the upper left, a curve in the upper right, and in the middle I've got this nice little parabola. So let's graph that. So the upper right, I had this curve. The upper left, I had this curve. And in the middle, I have this parabola type shape. Okay, so get your blueprint first by marking all this information, and then go to your calculator to determine the curves. Okay, so we've written down the information that we found earlier for this function. Vertical asymptote, we didn't have any. X-intercept, y-intercept, horizontal asymptote. I've marked that information here on our graph, which doesn't give us much to work with, but they're not going to all look alike. Go to your calculator, put it into y equals, let's graph it, and we don't get much here on the graph, but let's just sort of take this and put it on our axes that we have. It looks like it's here at the negative 1/3, and then here, I think it was at 3. So what's happening here is that the graph is going to ride below the horizontal asymptote on the left. It crosses over here at 3 and then rides above the horizontal asymptote on the other side. So let's try to mimic that on the document. Okay, so it looked like it's just going to ride below the horizontal asymptote on this side. Over here, it's going to come up and ride above the horizontal asymptote. That one's kind of awkward, but again, they're not going to all look alike. Let's check out our last 2 examples. All right, so let's take a look at this population growth. So the Game Commission introduces 100 deer into newly acquired state game lands. The population of that herd is modeled by this rational function. And t represents time in years. So t has to be greater than or equal to 0. That's our time. All right, we want to graph this model. So take a second, let's put that into your calculator. Let's check out what the graph looks like. So I went under y equals, typed in my function. Make sure I type that in right. 25 plus 3x, 1 plus 0.04. Okay, I did. Now, when you go to graph it in Zoom 6, you're not going to see anything. So I had to play with my window a little bit. First thing I did was I set my x-min to be 0. Remember, that's my time. So I let time start at 0, and I let time go up through 100 years. Then I looked at my y values, and I had to play around with those to try and get it into view. So I put my y min at 0 and my y max at 2000. So I could get what was going on with this graph in my window. So those settings will help you to see the graph. So here is the picture I get. So the first part of this question was to graph it. So there is our graph. Excuse me again. Now we want to find out what's the population of this deer herd when time is 5 years, 10 years, and 25 years. Well, how about we go to the table? And let's see what happens at 5 years. Okay, so at 5 years, we have approximately 333 deer. Notice at time 0, it's 100, because when no time has passed, there are 100 deer that are introduced. So after 5 years, we now have that herd size of 333. Let's see, at 10 years, the herd is up to 500. And at 25 years, the herd is up to 800. So those are the values for t equal 5, 10, and 25. And I totally forgot those numbers. Let me put those in there. 25 was 800, and I think the other one was 500. 800, 500, and 333. So we have 800, 500, and 333 for those different years. Okay, last question is, what is the limiting size of the herd as time increases? Let's check out the graph. Yeah, let's go over here, and I'm going to press the trace button. We'll look at this 2 different ways, but let's trace. Notice that the herd size is obviously increasing. We saw that, but there's going to come a point in time where it levels off, because we can't have a population continually increasing. Disease and predators will come in and keep it in check. So let's watch that Y value as we go further to the right. Come on, trace for me. So what am I at? Like 1100 there. Let's just keep going. We're going to get to a point where it's not really increasing much. So to determine the limiting size of the herd, see, those values are increasing a lot less as we go farther, or as our years progress. Let's check out the table. And let's just go down on our table. We're going to see it get to a point where it just sort of stabilizes and it won't get any higher. So let's keep going until we see some numbers that are just going to basically repeat. See, it increases at much smaller amounts as we go further to the right, as our X values get larger. Looks like we're getting close to, we're at 1402 now. I'm going to show you how to find this algebraically from our equation. Just keep going. You're not happy with that, are you? Okay, so this is showing me that my herd size is getting to a point where it's going to stabilize. And I don't want to do this anymore. So let's go to the equation. Let's find the horizontal asymptote for this equation. First, I'm going to go ahead and distribute that 20. So 20 times 5 would be 100, plus 20 times 3 would be a 60t, divided by 1 plus 0.04t. The polynomials in the numerator and denominator have to be written in descending power, so this is 60t plus 100 divided by 0.04t plus 1. So all I did was rewrite the function by distributing the 20 in the numerator and then writing it in descending powers. Do you remember how we found the horizontal asymptote? The horizontal asymptote is going to be our limiting size to this herd. We take the leading coefficients. Since the degrees are the same, let's take 60 and divide it by 0.04, the ratio of those coefficients. So 60 divided by 0.04, if we come over here, 60 divided by 0.04 gives me 1,500. So if I would scroll on my graph, remember when we had the graph and we were tracing it? If I go further, then I'm going to see that the limiting size of my herd is 1,500. It's not going to go any higher than that. So the limiting size of the herd as time increases is 1,500. All right, let's wrap it up with one more example. Last example, it's an application on providing food for a species of moth and looking at the quantity of food supplied versus the quantity of food consumed. It's a rational function, and the first thing we want to do is graph it. Now, when I go and put it in my calculator, obviously I'm going to put the numerator in parentheses, the denominator in parentheses. Let's find the horizontal asymptote because it's already in the proper form. And so the horizontal asymptote, since the degree of the numerator is equal to the degree of the denominator, it's going to be the ratio of 1.568 over 6.360. Let's find that value. It was 1.568 divided by, what was it? 6.360. So the horizontal asymptote for this graph is 0.2465. 0.2465. So that is the horizontal asymptote. So when I went to graph this, I adjusted my window to take into account that the x value should be greater than 0 and that my horizontal asymptote would be at this relatively small number, 0.2465. Okay, so if you want to look at my window, my x-min was at 0, my y-min was at 0. I put my y-max to be 1 because my horizontal asymptote was at 0.2 something, so I didn't want my y values to go too high. So notice we've got this curve, and there's a limiting value here, which is our horizontal asymptote. And if I traced it, or if I went to the table, I would notice that as x increases, the value of y is approaching 0.2456, which is that horizontal asymptote. Okay, so the question is, at what level of consumption will the moth become satisfied? The value would be 0.2465. That is our horizontal asymptote. So we've got the graph looking to where it stabilizes or levels off, gives us this value right here. So let's interpret that. X is the quantity supplied and Y is the quantity consumed. So when you supply the food, the maximum amount that's going to be consumed is the 0.2465